Alright, hi again guys. Welcome to the third video of the Exploring Quantum Optics series. Exploring Quantum Optics Lab. This isn't a YouTube series. Feels like it is. One thing I forgot, so we didn't really get up to polarization vectors last time. So I had kept everything in component form, but written with unit vectors. So something like that. Okay. So the idea is, we can just put that in a matrix form, and we just have, this. So that's it really. It's just a column vector. So you should have been working through questions in chapter 2. You might have gone past the classical stuff. That's good. Yeah, so I think we would have already met by now, and yep, I would have guided you through a lot of this stuff already. So one thing I'll point out is that the typo that I forgot to correct in the last video, but hopefully I've uploaded a new manual, so hopefully it's not even relevant anymore, is the polarization vector here. That one should actually be the amplitudes, with the y1 having a phase shift and some arbitrary phase shift, it might be 0, and then they both have the wave vector factor as well. So they both have this. This is like the shared phase, think of it that way, because it's light of the same frequency. Well, it's components of light of the same frequency, and then you have a phase shift on one of the components, which I hope you've already seen can lead you to circular polarizations, elliptical polarizations, and where, if you're watching the polarization vector come to you, it's actually rotating in the XY. That's a circular, but it might also be like this, elliptical. So this arrow is sweeping every period. So that's sort of the theory I wanted to get across. And then the idea is, when we have these polarization vectors, we can move this and start talking about a quantum state, which we usually denote by psi, and we write it in these things called kets, which are they're kind of like vectors. You can think of them as vectors for now. As far as we're concerned, they're going to behave like a vector. So let's write this for some x and y. The only difference is we don't really take into account when we had the electric field vector, we talked about the amplitude of a wave, right? And this could vary. We don't really have, because we're talking about, for example, a single photon, we are going to be talking about a single photon state, and the polarization of the photon, it doesn't really have an amplitude anymore, okay? It just has probabilities of being in different polarization states. So let's say our state is H, okay? That just means we have a photon. It can't have any bigness because it's sort of like a single particle. It's the smallest quanta of light you can have, okay? So we don't have an amplitude of the photon. It's just a photon. And the question is, which direction is it polarized in? So we've got y and x. It's coming towards us. We know that our photon is polarized like this. That's what we call H. We could have called it x before we were calling it x. Now we're going to use H for horizontal and V for vertical. Okay, so that would be a V photon, this would be a H photon. And I'll probably start drawing the axes like this. H, V. Alright, I'll try and keep this one short because the other two went quite long. So now you've got all the quantum theory to go through, and I'll just talk about the bits that students seem to have problems with. Okay, so this is your state. This is, what state is this? Is a question, right? So I've got equal what we call probability amplitude I'll show you what that means. The coefficient, just say, of h and v is the same. So I've got equal parts h and v, I've got this, right? Which we could also write as a 45 degrees, okay? So it's just like what we were doing before, but we're expressing it in a quantum framework, and we're describing single photon states, okay? This phi is what we call the state. These are also states. This is the phi state is a linear combination of being in a h state or a v state. And all the states are essentially like vectors, okay? So say we want to find if the particle is in a h, well, the photon, let's not use the word particle because it's misleading. It has particle qualities and it also has wave qualities, as we're going to find out. So it's not really correct to use either. It's just a photon, and this is how photons behave. So that's our state. That's a photon state, a single photon state. And we're saying it can be expressed in h or v. All right? It's either h or v. Well, actually, that's not quite the right interpretation. Okay? But it's a linear combination of h and v. Sorry, I've said the same thing like 100 times now. Let's move on. So, if it's a linear combination of both, there must be some kind of, if I measure it, it can't be both, right? I'm going to measure it, and I'm going to see it to be one or the other, I assume, or something in between. So say I've got my single photon state, phi, and that's incident on one of my polarizers that we've got over there on the apparatus, okay? So I've set my polarizer to vertical, all right? So and I'm measuring a lot of these states, which we call an ensemble. So there's an ensemble of, hundreds of phi state photons coming in. So a phi here, and a phi here, and a phi here, and they're all on their way to my polarizer. So how many am I going to pick up here? If I've got 1,000 on their way, how many am I going to detect here on average, okay? So what we do is we do this. So this is the bra, and we dot that with a phi, with the psi, sorry, not phi, psi. That's the Greek letter. And we take the modulus squared, and we've defined this to give us a probability, okay? So this, when you dot the bra of whatever state you want it to be in with psi, and you mod squared, this will definitely make more sense if you've read through the manual, so I hope you've already done that. If you haven't done that, go and do that and come back. The two should be used together. So then I go 1√2 VH. These are orthogonal, so that's just 0. Plus VV, that's 1. And then taking the square. And remember, this is a modulus squared. We don't have any complex components, so it's the same as squared in this case. But it's not just squared, it's absolute value squared, which means times the conjugate, complex conjugate. So I get a half. So that's sort of common sense. I set this to V. On average, I'm going to detect half of the photons. They're going to make it through. If I had it on H, I'm also going to detect, on average, half the photons. What if I put it on 45? Okay, so that's another question. Maybe you can work that out. If you write 45 equals 1√2 H plus V, right? So that is the state we've got. So that this is actually plus 45. That's the 45 degree state, which I wrote here, okay? So that's not surprising. So what is the probability of me measuring plus 45, given that it's in a plus 45 state? What is that? Okay, I'll leave that to you to work out. So it's important to get a handle on this stuff, because this is essentially all the tests we're going to be doing. But you got to understand what's happening. All right. So next. So the other thing students have a lot of trouble with is product state. So let's just talk a little bit about that. Okay. So the idea is if I make a product state, what do I consider here? H and H, the direct product. So I've got these two vectors. These vectors exist on a two-dimensional space, right? On the H and V space. Or equivalently, 45 and negative 45 space, okay? So I still have, this is just a change of basis, right? I can express any vector along here, say this red one, in terms of H and V, or in terms of 45, negative 45. It's just got to be a vector and it's orthogonal vector, okay? So this would be, you know, like a bit of H, like that, and then a bit of V, like that. This one would be probably no 45, because it's orthogonal to 45, and it would just be a negative 45, right? That's how I describe this in the 45 basis, all right? So then what happens when we take a direct product, this thing, of two vectors, okay? So this is different to an inner product, which is what I was doing when I was taking the probabilities here. So this thing, that's an inner product, okay? And that gives you a scalar out. We get a number out. We take the inner product of two vectors, we get a number. We take the direct product of two vectors, we get another vector, okay? And it's a higher order vector. So that becomes this. So we've got the, before talking about signal and an idler, we're always going to write the signal on the left, always going to write the idler on the right. Just let me pick this up. So we're always going to refer in our experiment to signals coming from the left side and idlers coming from the right side. That's just convention. So we'll always call this photon the signal, and we'll always call this photon the idler, okay? So that's what I mean. We usually, I think my convention in the manual is to refer to the signal photon, if I'm talking about general angles, as alpha, and the other one is beta, the idler is beta. So let's just keep that the same every time. So whenever we see something on the left, I'm talking about the signal. Whenever we see something on the right, I'm talking about the idler, okay? But we're not going to write S and I necessarily. Just remember, left is H, is our signal, right is idler. So watch this, it's still a vector. We've taken the direct product of two single photon vectors and made a double photon vector, okay? So this is four-dimensional. It's a four-dimensional basis. Now, a four-dimensional vector space, 4D vector space. This is just the maths. We're just defining the maths to help us calculate stuff in reality, okay? That's what it's for, to make predictions. You don't necessarily need to associate it with anything happening physically, but it's essentially just a way of keeping track of a two-photon state, okay? Two photons that are entangled need to be described together, okay? So 4D vector space. So what are the basis vectors? You might have just been able to see them. So there's a HH, because the initial vector is either H or V, and a HV, and a VH, and a VV. So those are this is a basis in that 4D space. Another basis is 45, 45, 45, negative 45, negative 45, 40 plus 45, and negative 45, negative 45, which is essentially corresponding to, like, you know, both photons being this, both photons being, well, one being plus and the other one, well, specifically the signal being plus, the idler being minus, the signal being minus, the idler being plus, and then both being minus, okay? And same with these, but instead of plus minus, we're just talking about H and V. Different bases, same as this basis and this basis, but in 4 dimensions, so we can't just draw a little Cartesian axis and visualize it, all right? Yeah, what's the time? 14 minutes, Jesus Christ, I don't know why does this always happen? Yeah. Anyway, you'll have time with me so we can talk about it some more. And yeah, so the example in the manual, this one, you can see I've drawn a crab claw here because that's essentially what's happening. You just, when you've got several vectors in a bracket and you want to direct product that with some other ones, the idea is each one applies to the other. It applies, so it's distributive. The vector's tensor product is distributive, so this one goes to there, and so does this one. it's just like multiply, but you don't get a scalar out. You get, each time you get a new vector of higher dimensionality, okay? Twice the dimensions. Unless you had 3 in here, and then if you had 3 vectors in here and 3 vectors in here, then you would get, 9 dimensions or whatever it is. Yeah. I think it is 9. Not sure. 3 factorial? 6? I feel like it would be more than 6. Anyway, it's something. Okay. Yeah, so this is some other terminology. Probability of one photon being whatever it is, given we're in some kind of state. Okay, so this is the terminology I'm going to be using. Probability of being in this, given we're in that state. And then some work for writing different bases, so you should do that. Yeah, operators, okay. So, all right, next video.